Now we will see what will happen to the pk model term. So the pk model, you are using bussiness. Again, bussiness will cause this problem here. So Reynolds stresses are replaced by your bussiness, which is 2 nu t Sij average minus 2/3 k delta ij and the mean strain rate term. This is the model term. Again, if I add it up, so expand this, I get 2 nu t Sij bar, or can write this as half of dou ui bar by dou xj plus dou uj bar by dou xi, dou ui bar by dou xj minus 2/3 k delta ij dou ui bar by dou xj. This last term goes away because of continuity, and I have essentially these two terms. So if I expand this, I get I have nu t dou ui bar by dou xj dou ui bar by dou xj plus nu t dou ui bar by dou xj dou uj bar by dou xi. This is sum of 9 plus 9, 18 terms. So let's expand it and see what happens to that. So if I expand this, I get nu t of dou u1 bar by, write it here first, nu t of dou u1 bar by dou xj dou u1 bar by dou xj term plus dou u2 bar by dou xj dou u2 bar by dou xj plus dou u3 bar by dou xj dou u3 bar by dou xj term plus nu t of dou u1 bar by dou xj dou uj bar by dou x1 plus dou u2 bar by dou xj dou uj bar by dou x2 plus dou u3 bar by dou xj dou uj bar by dou x3. If I now sum over j, I would get square of this, right, plus dou u1 bar by dou x2 square plus dou u1 bar by dou x3 square plus dou u2 bar by dou x1 square plus dou u2 bar by dou x2 square plus dou u2 bar by dou x3 square, and then the third term here, which is dou u3 bar by dou x1 plus dou u3 bar by dou x2 plus dou u3 bar by dou x3. Okay, sum of 9 terms for this, and again the sum of another 9 terms for the cross terms here, which is dou u1 bar by dou x1 dou u1 bar by dou x1 plus dou u1 bar by dou x2 dou u2 bar by dou x1 plus dou u1 bar by dou x3 dou u3 bar by dou x1. The second term on the right hand side part, which is dou u2 bar by dou x1 dou u1 bar by dou x2 plus dou u2 bar by dou x2 dou u2 bar by dou x2 plus dou u2 bar by dou x3, dou u3 bar by dou x2, right, and then the last term, which is dou u3 bar by dou x1, dou u1 bar by dou x3 plus dou u3 bar by dou x2, dou u2 bar by dou x3 plus dou u3 bar by dou x3, dou u3 bar by dou x3. Okay, 9 plus 9, 18 terms. Luckily, most will go away. Okay, we have to expand it to get rid of it in the stagnation zone, but all these terms exist in a regular flow, in a where you don't have such considerations. So, what terms go away here? We have all the rotational strain terms. This one, all the rotational strain, u2 x3, u3 x1, 3 x2, right, and then this survives. You have this, okay, it is small rotational strain. So that means I get finally pk model is equal to, so this was pk exact, right, pk exact was almost 0. Now we have pk model is equal to nu t of, so have 3 plus 3 6 terms, which is essentially 2 nu t if I take, because this dou n bar by dou x1 is repeated here. So I get 2 nu t of dou u1 bar by dou x1 square plus I have dou u2 bar by dou x2 term, so which is dou u2 bar by dou x2 square plus dou u3 bar by dou x3 square. And is this 0 in a stagnation zone? What is it? Extremely large, right? So this is like super large. So this is approximately equal to very large, right? Much bigger than the font size here. So this value becomes super large in the stagnation zone. So what is your model is telling is completely opposite to what it should be in reality. So you need to do something about it, otherwise you will get unphysical, unrealizable results at the end, right? So there are two directions for to fix this particular part. One is an explicit method, the other is an implicit method. Is this clear so far before we go into a solution? Okay. So basically we looked into a stagnation zone where there is a local isotropy, and also the rotational strains are small compared to irrotational strains. That is what that's what occurs in a stagnation zone, and we see that model is predicting very large values, because you are essentially going after strain. In the Boussinesq, you essentially related your stress to the strain, and this is the consequence of that. Okay. So there are two methods to have a solution here. One modeling option is to go after a limiter for the production rate of turbulence kinetic energy, a pk limiter, and this modeling option you can say or call it explicit method, not to be confused with any CFD techniques here, explicit, implicit methods. But what I mean by explicit is explicit implies explicitly controlling pk in the k equation. You directly go after what is called a pk limiter. Okay, so what we look at is called a pk limiter. Because pk is going very large, you need to enforce a limiter for that one. Okay, and these are explicit because you directly use it in the k equation. So there are many production limiters, pk limiters. For a k epsilon, for example, for a k epsilon model, you can get the pk is set as, that is the pk model will be set as a minimum of whatever you are computing from the model. So you just have to add an extra line in your code, comma, you have a cpk epsilon. So your production rates are becoming very large because of large irrotational strain, but I will transfer this to the dissipation rate, so that there is a, the balance between the pk and epsilon. So I am going to take the minimum of these two, pk being set, let us say some coefficient times epsilon, but the cpk requires some optimization. So user dependent value, that is a downside here. Okay, so the downside is that cpk is user dependent. Okay, or you can say flow dependent, so some optimization is required here. Flow dependent, not flow dependent, I wouldn't call it flow dependent here, you can say some optimization is required. Okay, so for the pk limiter, this could be one option. You can play with it to see whether you get a good value. In a k omega SST model, Mentor suggested a limiter for it, which is pk equal to minimum of, again the pk model value, or you take 10 times the beta star k omega value. Okay, so this is coming from your, the reference for this is (1993, 1994). So this is, you take minimum of whatever is computed, or 10 beta star. Beta star, if you remember, is also a constant there, k omega value here. And k epsilon also got a correction from the original group which made standard k epsilon at Manchester. So this is called Kato-Launder correction. Okay, so for a k epsilon also you can do another option, which is the pk model itself. You are computing, not take this min function, but look at, use the rotation rate here. So the strain rate caused a problem. So instead of that, they want to use rotation rate into the pk computation. So nu t square root of 2 Sij Sij, and then you look at 2 omega ij omega ij. Omega ij is the rotation rate tensor, if you recall what it is. Okay, so omega ij is the mean rotation rate tensor. So including this will cause pk to be better. So this particular correction is called Kato and Launder correction. So this is Kato Launder. It's 1993. That's a reference for this. So these are explicitly controlling. You put a main function, or you directly compute pk model using another formula. So basically you are attacking the k equation, then it is explicit. If you are not, if you are going after epsilon equation, then it becomes implicit. Okay, k is untouched, you correct everything through epsilon implicitly. Even though the unphysical behavior is in the k equation, you can control it using epsilon or the second term. So the implicit method is modeling option 2 or realizability constraints only. An implicit technique, implicit method implying controlling excessive pk through epsilon equation. Right. So this particular option is basically, you would have a time scale limiter here. Okay, if you look at time scale, you have a k by epsilon ratio. So in implicit techniques, you usually use a time scale limiter or a turbulent time scale, right? Turbulence time scale limiter. So for a k epsilon model, for example, you can look at this tau can be, for a k epsilon model, you can have implement, after all you compute k and epsilon, you can set this time scale as take minimum of k by epsilon, or you take 1 by 3 c mu lambda I. Lambda I you would know from the this Durbin's reliability constraint, right? So that you can use it here, lambda I. Okay, the lambda I is the square root of 2/3 Sij bar Sij bar, or for a k omega, it will be minimum of your 1 by omega or 1 by 3 lambda I for a k omega model. Both of these techniques are used, explicit, implicit corrections, to limit the excessive production rate if you have stagnation type of flows in general, okay, to make it sure. So this completes the realizability constraints, and as I mentioned, there are realizable models. One of the examples I have already uploaded in the Moodle. You will see there is a realizable k epsilon model. One can also implement that. If you like that model, you can implement it. Or if you already have implemented, let's say k omega, and you are just going to implement these limiters to make sure that the model behaves physically, that is also a perfectly good choice. And I will show you some results what can happen. Sometimes this realizability constraints can give good results, making flow realizable. So this is an example of Durbin's realizability constraint. So the wake is expected to be unsteady, oscillating, but when we just use, let's say, a k epsilon model without any condition, the wake is completely steady. No matter what we do, it is not oscillating at all. But by implementing that Durbin's constraint, then we get this wake starts to be unsteady. So it gives you good results, even though this flow, you see that there is no stagnation zone here, but still it helped. Stagnation zone, definitely it will have an impact. In general, it's good to use these constraints just to make sure that the unphysical part is eliminated locally if it is present in the flow. So these are good and easy to implement, just an added extra line in the code. Okay, and in spite of all this, of course, this now completes the entire eddy viscosity model. As I said, we will not go into every other type of eddy viscosity model. There are many, but you would figure it out yourself, any other model that is there. I have covered majorly the K epsilon, RNG, realizable, and then low Reynolds number, high Reynolds number, all this major part. And despite all this, sometimes you will see that the results are not good. Okay, that's inherently you're using Boussinesq. You're taking Reynolds stresses, which is completely random component. The stochastic behavior of turbulence is modeled as statistical. That is dou u bar by dou x2 terms and so on. You are looking into a mean strain instead of a stochastic component. So that Boussinesq itself will not give you good results many times. And I have an example here I can show you. This is from our own results. So here this is a dense phase carbon dioxide, right? So it's a heavier than air, and its dispersion. So I'm essentially looking into the concentration profile here. The y-axis shows the CO2 concentration, the x-axis is the distance. So you can see the experimental values are these open squares, and these three other are standard K epsilon, SKE, RNG K epsilon, and realizable K epsilon models. Okay, so this it's a realizable K epsilon model. We did not implement realizability constraint on a standard K epsilon. This is actually a realizable K epsilon model. So you see all three are behaving far away from the experimental data. This does not mean that this is the behavior in every class of flow, right? But in this particular situation or in general, you will see that there is a limitation of an eddy viscosity model, how far it can do good. Sometimes you just need to switch to a complicated model or even go to an eddy resolved technique. Okay, you have reached the limitation of eddy viscosity modeling. Regardless of changing K epsilon to K omega or anything, it will not yield any great result. With so much assumptions that we have made, sometimes results are not good, and these are like practical cases, right? It could be like life and death here. I mean, if you believe eddy viscosity model and say that the concentration is low here, okay, and I will go and walk, and you are dead. The actual experimental value is twice that of what the eddy viscosity model has predicted, right? So it's about, I think, 6%, 6% volume fraction CO2 is like the life and death value. I think you will be unconscious, maybe 8% you are dead, okay, and this is like 20% in the experiments, right? This is predicting like 10%. So if you want to take chances, it's an individual choice, right? So this exists. So that means I am pitching for that there is a need to go into models that are much more complicated and giving much better accurate results. Okay, and we see this also in, I think I have another slide. Yeah, this is even more very industrial problem like atmospheric dispersion. This is like very large case. This is actually actual topography. You have some hills and mountains, valleys and so on, some buildings. An actual case actually is not hypothetical. It's taken, one can download such a map and reconstruct in CFD, and this is a chlorine dispersion. You can have pipelines carrying or some industrial facility where there is a leakage, it can happen. So again here, the experimental values are way up compared to all the three, standard K epsilon, RNG, realizable, or giving nearly the same behavior, only a marginal 5-10% difference in their behavior, but the experimental values are so large here. So that will be there at the end of the day, okay, right. Of course, one should also see the cost benefit. Eddy viscosity models are cheaper, it's faster to run, stable, numerically much stable, and you are assured of results rather than getting no results. So there is always this cost benefit one has to look at. So in the next class we will start the Reynolds stress modeling. We will go to another class of models.